What if the ground beneath one of America's largest dams is moving? A silent shift, 23 feet, no explosion, no earthquake headline. Just the earth, quietly changing position beneath millions of tons of concrete and water. And tonight, you're about to see why scientists are watching this place very closely. Lake Oroville Dam, California's tallest dam. A structure holding back more than 3.5 million acre-feet of water, enough to supply millions of people. For decades, it stood as a monument to engineering confidence. Then something strange appeared in the data. Not a crack, not a leak, a shift. Deep ground measurements showed movement. A horizontal displacement measuring roughly 23 feet across monitored terrain zones near the reservoir region. Not overnight, not violently, but undeniably. And when land moves where it shouldn't, scientists like to start asking uncomfortable questions to understand what might cause land to shift. You have to look beneath the surface, far beneath what your eyes can see. California sits on one of the most geologically restless regions on Earth. The Pacific Plate and North American Plate grind past each other constantly. That friction builds stress. Stress looks for escape routes. Sometimes it releases in earthquakes. Other times, it moves quietly. Experts studying the Oroville region consider several possibilities. Fault movement. Small, slow-slip fault lines can creep without triggering noticeable earthquakes. These movements may shift ground gradually over years. Subsidence. When underground materials compress or groundwater levels change, land can sink or tilt. Reservoir-induced stress. When millions of tons of water fill a reservoir, that weight presses downward. Water can seep into fractures, altering underground pressure and lubricating faults. Tectonic strain transfer. Stress from distant seismic activity can subtly redistribute forces underground. Each explanation alone is plausible. Combined, they form a puzzle. And puzzles under dams demand attention. Geologists don't panic easily. Their job is to study slow processes that unfold over centuries. But when ground displacement is measurable and ongoing, it triggers investigation. Because dams are different from ordinary structures, they rely on absolute stability. Even small shifts in foundation geology can affect stress distribution across concrete, spillways, and support rock. Engineers don't just ask, is it safe now? They ask, will it still be safe in 10 years? 20? 50? Monitoring stations around major dams constantly record ground motion tilt angles, internal pressure, micro-seismic vibrations. Not because failure is expected, because prevention depends on early warning, and subtle movement is often the earliest signal nature gives. Imagine standing at the base of Oroville Dam. Above you rises a wall taller than a 70-story building. Behind it, an entire inland sea. If underground forces were to accelerate, engineers would worry about three things. Foundation, stress redistribution. If the rock beneath shifts unevenly, pressure concentrates in unexpected zones. Spillway alignment changes. Even slight ground tilts can affect water flow paths during heavy releases. Seismic amplification risk. If stress builds along a nearby fault, stored strain could release suddenly. None of these mean disaster is imminent, but they are the exact scenarios structural geologists are trained to anticipate, long before the public hears about them. Because with dams, warning signs don't always arrive loudly. Sometimes they whisper. History has shown that massive structures and geology don't always cooperate. In 1963, Italy's Vajont Dam didn't fail structurally. The mountain beside it collapsed into the reservoir displacing water that overtopped the dam and caused catastrophe downstream. In 1975, China's Banqiao Dam system failed after extreme conditions overwhelmed infrastructure and geological limits. And in California itself, the 2017 Oroville spillway crisis forced evacuations of nearly 200,000 residents. Not because the dam collapsed, but because erosion threatened its emergency spillway foundation. Each case taught the same lesson. The greatest danger isn't always the dam, it's the ground it stands on. Let's separate science from speculation. A 23-foot shift does not mean the dam itself moved, or 23 feet. It does not mean collapse is imminent. It does not mean catastrophe is underway. Measured displacement typically refers to geological survey markers across a monitored area over long periods. Ground can move gradually without affecting structural integrity. Modern dams are designed with safety margins, flexible tolerances, and constant monitoring systems. In fact, the reason scientists detected movement at all is because surveillance technology today is extraordinarily precise. Satellites can measure millimeter-level ground motion from space. So the discovery is not proof of danger, it's proof that monitoring works. But scientists don't ignore movement, they track it, because trends matter more than single measurements. The scenario experts watch most closely isn't sudden collapse, it's acceleration. If ground displacement were to increase in speed, if micro-seismic activity began clustering, if underground pressure readings changed simultaneously, that pattern could signal stress building along a hidden fault zone. Not visible, not obvious, but powerful. In geology, rapid change after long stability is the signal researchers respect most, because Earth's crust rarely moves randomly. When it moves faster, it's usually responding to force, and force underground always has a source. Right now, teams of engineers, geologists and hydrologists continuously study data from the Oroville region. They analyze satellite radar measurements, GPS ground stations, seismic sensors, reservoir pressure levels. Every reading feeds predictive models designed to answer one question: is the system stable? So far, monitoring indicates no immediate structural threat to the dam, but surveillance hasn't stopped. In fact, it's intensified. Because modern infrastructure safety isn't based on reacting to disaster. It's based on detecting change before disaster is possible. The surface of Lake Oroville looks calm, silent, motionless, but far below, the earth is never still. Rock shifts, pressure builds, faults adjust, forces older than civilization continue their slow work in the dark. And tonight, as you look at that tranquil water, just remember, the most powerful movements on Earth are the ones you can't feel yet.